Good afternoon, everyone. Hi, my name is Ray Wang. I'm a senior product manager on the AWS Batch and High Performance Computing team. Today with me, we have Michael Raposa. He is the head of platform engineering at AQR Capital. So today I will be talking to you about AWS Batch. I'll give you a little brief overview of Batch, and then move on to some of our recent announcements that we made in 2018. And then I'll talk a little bit about our roadmap for 2019 before handing it off to Michael to discuss how AQR Capital is leveraging AWS Batch to identify new investment signals. All right, so AWS Batch is our cloud-native job scheduler. It is a fully managed service, which means that you don't have to download any software and there is no servers to manage. We really want you to focus on your job and just tell us the requirements of your jobs, what kind of application you like us to run, and it will figure out how to execute your jobs and how to manage the underlying infrastructure. So we want to take the undifferentiated heavy lifting out of you guys' lives. And AWS Batch is also natively integrated with many other AWS services. We think there's a lot of value in those services, such as auto-scaling groups or identity and access management. So we want to make it very easy for you to access those services through Batch. Batch also offers a cost-optimized resource provisioning, which just means that you can use EC2 on-demand instances, spot instances with Batch with no complexity at all. And if you have already purchased reserved instances, then you can use them with Batch also. Of course, there is no additional charge to use AWS Batch. You only pay for the AWS resources that you consume. For example, it might be EBS volumes or EC2 instances. The Batch itself is free. So in 2018, we made several announcements. So first, for regional expansion, we have expanded to 5 new regions in 2018, including Mumbai, Seoul, Paris. And now AWS Batch is available in 15 commercial regions. And we don't plan to stop here. We're definitely going to continue to expand to new regions. And in 2018, we also made a number of features that enhances the performance and manageability of AWS Batch. We have integrated with Amazon CloudWatch events. And so Batch, now you can set Batch as a Amazon Cloud event target. What that means is AWS Batch, we can trigger the submission of a job to AWS Batch respond to any event pattern or on any schedule. For example, it's now very easy for you to submit a lot of jobs to Batch every 9 a.m. on weekdays. Or you can submit a job to Batch whenever you have an end user who drops a file into a S3 bucket. Another feature we launched this year is called Job Execution Timeout. This is a feature designed to help you control your cost. Because for example, if your jobs, they normally run for 10 minutes, and there's probably something wrong if a job is running for 20 minutes, then you can actually set a job execution timeout duration to be 20 minutes. So Batch will automatically terminate your job after 20 minutes is up. So this definitely will help you manage your costs a little bit better. And if your organization uses AWS CloudTrail for compliance reasons, then Batch is now integrated with AWS CloudTrail, so you can audit your costs to AWS Batch APIs. And last but not least, we made a number of significant scheduling and throughput enhancements. So now Batch schedules jobs, it's getting faster and faster, and we can handle millions of jobs with ease. So in addition to the performance enhancements, we also worked really hard to improve the managed compute environment experience. For example, you can see that we just added support for a lot of new instance types, such as the Z1D and the R5D. And we also, about 2 weeks ago, made an announcement that we will support EC2 Launch Templates. So Launch Templates is a very powerful and flexible way for you to templatize your EC2 launch request. And through Launch Template, you can do things like you can increase the size of your container volume, you can encrypt your container. We also support customer user data. This is very powerful. You can do things like you can mount an EFS on instance launch without the need to create your own custom AMIs anymore. So custom user data is very powerful, and we encourage you to try it out and see what use cases you can come up with. So about 2 weeks ago, we also made a very big announcement about this new feature called Multinode Parallel Jobs. But before I talk about Multinode Parallel Jobs, I want to briefly review how AWS Batch handles your jobs. Right? So when you submit a single job to AWS Batch, what is happening is that Batch will take a look at the job's requirements and will scale up an appropriately sized instance to run your job. So here's the instance. We'll create a container within that instance, and we'll run your job inside of the container. So if you submit lots of jobs to AWS Batch, we'll take a look at the requirements of all those jobs, try to bin pack them into as fewer container instances as possible, create all the containers for each job, and run the jobs in there. But the thing to call out is the largest job you could run with Batch prior to multi-node parallel jobs, it has to fit into a single container instance. The instance might be very big, but it still has to fit into one. So with the support for multi-node parallel jobs, this all changes. So now you're able to submit a job to Batch that spans across multiple instances. In this example, we have 4 instances up for this single job. What Batch will do is Batch will create a container in each instance, and then we'll run the jobs in all the containers. AWS Batch will also help you set up networking so the instances and containers can communicate with each other to run your job. This is perfect for distributed computing workloads. For example, if you have a tightly coupled high-performance computing workload, such as weather simulation or computational fluid dynamics workload that uses the MPI framework, the message passing interface framework, you can now run these MPI jobs on Batch. This is also very good for distributed machine learning and deep learning. So if you have a distributed TensorFlow workload, this is also great. So for a roadmap, what can you expect in the next 12 months? So first, we will soon announce the support for the Elastic Fabric adapter. So EFA is something we just announced on Monday. It is a new EC2 network device that will help enhance the performance of distributed high-performance computing workloads. So if you have MPI jobs, this is perfect for that. So you could use Batch to submit your MPI jobs, process your MPI jobs, and use EFA to increase the performance. We will also significantly improve our Batch console and also emit CloudWatch event metrics for monitoring the status and health of your jobs. For those of you who have GPU-accelerated workloads, we'll announce some better GPU support very soon. Of course, we're going to continue to make scheduling and performance improvements. That includes support new instance types as soon as they launch, and also support any new regions when they announce. These are just some items that we have planned for 2019. I'll be happy to talk to you afterwards if you have more questions. Now I'll hand the stage to Michael. Here we go.
Thank you. So I have a lot of content to cover, so I'm just going to dive right in. First, the legal and compliance team at AQR says hello to everyone in Vegas. You can read these disclosures at your leisure. So our agenda, I'm going to talk very briefly about AQR and what we do, and spend a little bit more time on the business problem that we face. And that'll sort of frame the discussion for the rest of the talk. And then spend most of my time on the actual solution, the lessons learned, and the takeaways. If I have a goal for this talk, it's for you to walk out of this room learning from our mistakes. So if you go ahead and build this high-performance compute cluster on Amazon Batch, you've learned from our errors and can move forward and build your own solution in a much faster manner. So first, AQR is a quantitative asset management firm. We're based in Greenwich, Connecticut. We have roughly 1,000 employees. Close to 50% of those employees have advanced degrees. And as of September 30th, we had $226 billion of assets under management. So background. So as I mentioned, we're a quantitative asset management firm. And what that means is we make our investment decisions driven by numerical models. We're a quant fund, to coin a phrase. Researchers working for us develop these models to describe various markets. So they may develop a model to describe equity markets, and then backtest those models going back several decades to validate those models. And then these same researchers have a never-ending appetite for more data. So as more data comes in, they can use that data to add additional factors, additional features to the models that we have, and hopefully fine-tune performance. So what does that workflow look like? So here I'm going to describe a workflow for a typical researcher. It's purely illustrative. It doesn't describe exactly what AQR does. I'm greatly simplifying it here for this particular presentation. So a researcher starts with an idea. Maybe his idea is earnings per share is a good indicator for future performance of an equity. So he goes to our databases that we have. He gathers up the data to describe earnings per share and equities and all of this historical data. He fires up his local development environment, let's say in PyCharm, developing in Python, and builds a model to describe his idea. So again, maybe he's thinking earnings per share is a good predictor. He tests that model locally on his development environment to make sure it's syntactically correct, it compiles, it runs. And then the next thing he wants to do is validate that that model is actually a good idea. So he back tests it. So instead of just testing locally on his machine, he may want to test 20,000 equities going back 10, 20, 30, 40 years. That's where the cluster comes into play. So he wants to submit that job to a big cluster on the back end, which parallelizes that job across all the nodes that are available. And then finally, analyze the results. So the cluster finishes analyzing the backtest, or the cluster finishes running the backtest. The result is given to the researcher. He analyzes it, determines if there's any merit to that particular model, and then iterates on the process. Maybe earnings per share isn't a good predictor. Maybe if he adds market capitalization to the model, that would be a good predictor. And again, he goes through that process again of gathering the data, building the model, backtesting, et cetera, et cetera. So the problem that we have, on-premise compute grid can't keep up. So as we continue to grow, as we add more researchers, they're constantly adding more backtests, more compute resources to the grid, and the grid can't keep up. CapEx ends up being locked into those grid resources. So as researchers go home for the weekends, in the evening, the grid basically sits idle, and we have dollars now invested in that grid that are effectively doing nothing. Researchers are waiting for grid resources, so they're waiting in queue. The longer they wait in queue, the longer it takes us to develop a new signal, and the longer this entire process takes of that feedback loop in the prior slide. A corollary to that is researchers need to get job results quickly. And then finally, we have new experimental use cases, especially around GPU, that require a significant upfront capital investment that we don't want to make that investment for just an experimental use case. So what were our design considerations? We wanted the solution to be scalable both in compute and memory. And then along with that solution, we wanted it to be fast without long queue times. So we wanted a researcher to be able to submit a job and not have to wait in line behind another researcher in order to get his job into the running state. We didn't want to manage a job scheduler. So there's a lot of high-performance compute job schedulers out there like Condor, Slurm, Sun Grid Engine. We found them extremely difficult to maintain and support. The Condor manual itself is over 1,000 pages. We didn't want to have to dedicate resources in order to support a job scheduler. And we wanted it to be very easy to use. So we wanted researchers to be able to develop their model locally on their workstation and then submit it to the grid in sort of a seamless manner. We didn't want to have them go through any sort of pre-processing step or pre-staging step or putting the data or the code in a particular place in order for the job to run on the grid. And then, of course, we're a financial institution. We wanted this solution to be secure. And we wanted that security issue to be an issue for the cloud engineering and the InfoSec team, and not necessarily an issue for the researchers themselves. So here we are at reInvent. It goes without saying that we built this solution on AWS. We built it because AWS provides that burstability that we need. We leveraged as many building block services that AWS provides in order to build this solution as quickly as possible. So we leveraged services like Amazon S3, Amazon Batch, EC2, ECS, Kinesis, et cetera. And then we also leveraged Spot. And we'll get into how much it costs us to actually run on Spot, but it's significantly less than running the on-premise grid. We wanted a seamless interface, so we based that interface on Sun Grid Engine. If you're familiar with Sun Grid Engine, you may be familiar with commands like qsub and qstat. We created similar commands called bsub and bstat. And we picked Sun Grid Engine because they do a very good job, and we wanted an interface that was familiar to researchers. We created a submit jobs API using the AWS command line. It basically allowed them to submit jobs via a CLI or an API, which gave them unlimited compute at their fingertips. This is for the researchers. And then a short feedback loop, so jobs got to the start state as quickly as possible. And then most importantly, to me at least, having worked in IT for 20 years, is we wanted the back-end environment that the researchers are running their jobs in to match their front-end workstation where they're developing their jobs. It's very frustrating to have a situation where a job runs in one environment, i.e. your workstation, but then as soon as you submit it to the grid, the job no longer works. Those are always difficult issues to take care of or resolve. We want it to be very fast. We automated everything in the environment. We leveraged infrastructure as code to deploy our solution and also to manage it. We basically gave, in quotes, unlimited compute, and we'll get to why that's unlimited, in quotes, in a few slides. And we wanted very short start times. So we wanted a job to be submitted and to be running in the running state within minutes without long queues for the researcher. And then we wanted the solution to be secure. We did encryption everywhere, which isn't the best of security controls, but in the cloud, AWS makes it very easy to just sort of check the box and get encryption. We leverage as many AWS security controls tools as possible. So we use things like KMS, guard duty, IAM. And then, as I said before, we made security a cloud engineering issue and not a researcher issue. We tried to make security as easy as possible for the researchers to just natively work in their environment. So now, let's get to the solution itself. So we start here in the lower right-hand corner with little gray men. Those are the researchers. They are remote desktoping, doing the RDP protocol into a Linux virtual desktop that's running on EC2. That desktop has an NFS mount point for their home directories, along with a bunch of temp shares and data shares that exist on EFS. And they log into that environment, they get a full desktop, they fire up PyCharm, they start developing their models, they test them locally, make sure that they work, and then when they have a working model, they submit it to Batch. And we've written a very lightweight wrapper around Amazon Batch that we call Batch Star that's used to submit jobs. So researchers are fairly non-technical users. We don't want to expose the entire AWS API to them. So we've simplified that by delivering this simplified interface, which we call Batch Star. And that takes care of bundling up the job and submitting it into Batch. And then after that, Batch does all the heavy lifting. So Batch then fires up all of our EC2 instances across 6 different availability zones, connects those instances to ECS, starts the containers, and then starts running and executing the jobs. We store our container images in ECR, and then we have a job state engine that orchestrates the jobs across the cluster running in S3. What's important to note here is that the jobs are executing in the same context that the user is running them in. So if a user is logged into a VDI as Joe Schmo, when the jobs execute on the back-end grid, they're also executing as Joe Schmo with the same user ID and GID, which means there's an NFS mount point, and that container has the same access to those files as the end user does who submitted the job. This is critical because it allows the output of those jobs to go to that EFS endpoint and still be accessible by the researcher when he wants to analyze the results. So what does this look like from the researcher's perspective? So this is the simple command that they need to run in order to submit a job to the grid. And you can see here it's written in Bash. There's a for loop there going from 1 to 25. They're executing a command, Python test my model, just sort of a made-up command. And they're piping that into this bsub command that we've created. And then once that command is executed, bsub is going to wrap up that command itself and submit it to Amazon Batch. Under the covers, Amazon Batch is going to spin up 25 different containers, and each one of those different containers is going to execute the command Python test my model. And the researcher could have just as easily have scaled this up. Instead of doing 25 containers, it could have been 2,500, 25,000, 250,000 containers. It doesn't really matter to us. The researcher also has control of how big he would like the container to be. So instead of, in the previous slide, you can see he could scale it out laterally, but now he can also scale out the container vertically as well. So he can set the number of CPU for each one of those containers. He can also set the memory. So we can go CPU all the way up to 36 vCPU, and he can set the memory all the way up to 128 gigs of RAM. Once he submits the job, he gets a nice little interface that basically shows him the status of the job. Each one of the lines in that output is an individual container that's running the Python test my model. It goes into the runnable state, and then when the job is done, you can see that it's actually succeeded. Now, some researchers have said, hey, the CLI is nice, but I would like an API as well, because I do all my development in Python, and I want to immediately, as part of my pipeline, go directly from development into job submission and backtest. And I don't want to have to now shell out to the CLI to submit my job. So we wrote an API that, again, wraps around the Amazon Batch. And the researcher instantiates a cluster object specifying a CPU and memory for each one of the containers. And then he has this function called CloudMap. CloudMap is exactly the same as the Python map function. If you're familiar with Python and that function, it takes 2 arguments. The first argument is a function. In this case, it's this made-up function called foo. And foo is just taking an input and raising 2 to that power, so 2 to the 0, 2 to the 1, et cetera. And then also a range, a list, an iterer. And in this case, it's the numbers from 0 to 9. So map in this case is going to call foo, and it's going to raise 2 to the 0 power, 2 to the 1 power, 2 to the 2, 2 to the 3, et cetera, et cetera, et cetera. Now, that, if we used map, the normal map, that would just execute locally on the workstation and then return the results to the caller. Here, we're using Cloud Map, and what that's doing is now bundling each one of those different calls and executing it in a container on Amazon Batch. So all of this is now executing remotely. Now, we wouldn't necessarily do this to raise 2 to a power. That's a bit silly. But you can imagine replacing foo with that test my model and running a back test. And instead of iterating between 0 and 9, you would iterate across 20,000 different equities. Researchers also came to us and said, hey, this is great, but what I'd like to do is I like to submit a job and then have that job submit additional jobs. So here we have an API where we're calling a job within a job. And then that function job within a job instantiates, as you can see there on line 29, instantiates yet another job that is being submitted to the grid. The benefit of this is now we're able to create direct acyclic graphs. So in this scenario, you have a researcher. He says, hey, I would like to backtest 20,000 equities going across 2 decades. So the first job that he submits is a job for each one of those different equities. So Apple, Microsoft, IBM, HP. And then each one of those jobs calls a child job that then deals with each one of the different years across all of those different decades. The beauty here is now we have this massive parallelism going on. We're basically executing 20,000 equities times 20 years worth of data. And that's creating an enormous number of jobs all at once. Each one of these jobs is then executing, then rolling back their results to their parent job, and then finally rolling back those results back to the calling client so the researcher can analyze the results. All right, so now lessons learned. First set of lessons learned is basically AWS 101. You're running a batch job, use the spot fleet as much as possible. For us, that's able to drive down costs down to $15 an hour for 1,000 vCPU. So basically $15 for 500 physical cores. It's an incredibly low price and something that we can't match on premise. Use as many instance types as you can so that Spot Fleet has as many options as possible to drive the lowest cost. We happen to use C5s, M5s, and R5s, which is also all of the instances that work for us and are layered on top of the Nitro hypervisor, which we've had a lot of success with working with. And then also, again, to lower the cost as much as possible, use as many AZs as you can. Log everything, ECS logs, job output, host logs, et cetera. And then also monitor everything. So if you build a solution like this, you're going to end up building a lot of custom metrics that don't come out of the box from Amazon. So you're going to want to track the job runtime. You're going to want to track the job startup time, so the time that it goes from start time to the actual job in the running state. You'll need to track job cost as well. This is something your management will always ask: who's using the most resources on the grid, who's charging or driving up costs the most. And then you'll also want to track high priority queue usage, because there's always that one guy in the group that feels he can cut the line and constantly use the high priority queue. So you want to track for that as well. All of this monitoring can then be used to develop CloudWatch dashboards. We use CloudWatch. You could use Grafana. There's tons of tools out there to visualize data. We use CloudWatch just because it's very easy to publish data into CloudWatch, but also publish data out of our logs into CloudWatch as well. So we monitor everything: the batch compute, the desired level, the CPU by user, et cetera, et cetera, et cetera. And the dashboards really just continue our EFS % IO limits, job completion by users, All of this information is useful to all of your L1 and L2 operations people that are going to be supporting the grid. Without these visualization, trying to diagnose problems is extremely difficult. So, more lessons learned. As we added more researchers, we started getting into the dreaded too many request exceptions. If you worked at Amazon or worked for Amazon in any length of time, you will run into this particular issue. And what was happening here is, as we added more researchers, they were calling this API called describe jobs to get the status of their jobs. Is my job running? Is it stopped? Has it succeeded? Has it failed? And as we added more researchers, they were making more and more of these calls, and we're getting these exceptions. The other issue that we're running into is governance guardrails, so making sure that researchers are doing the right thing. The solution to that was to build an event-based pipeline. So Ray talked a little bit about how Amazon Batch emits events into CloudWatch events as job state changes. So job goes to the pending state, the starting state, the finished, the succeeded state, or the failed state. All of those events get fed into CloudWatch events. We then have a Kinesis stream that listens to each one of those events, and then a lambda function that processes each of those events as they're coming through. And that lambda function is basically taking all of those events, adding a little bit of metadata to them, and then sticking them into DynamoDB. DynamoDB then has streams hanging off of that, and that allows us to now hook up a whole bunch of lambda functions that do a lot of useful things for us. So the first lambda function, a series of lambda functions, is the job policy enforcement. So this is the job engine that's watching for that user who's submitting too many jobs to the high priority queue, or a job that's been running for too long, or a job that's using the incorrect container. And that lambda function is now, if the policy violation is bad enough, going to terminate the job forcefully and or email the end user that submitted it. And then also we have this lambda function that's collecting all these metrics. So those metrics that you saw on the dashboard are now all being collected by this lambda function. So things like the cost of the job, the running time of the job, all of that good stuff is then being dumped into CloudWatch. And then finally, the researchers are no longer querying the describe jobs API. They can now query directly to DynamoDB. And DynamoDB allows us to sort of turn the dial and scale up as necessary without having to run into any throttling limits. Second set of lessons learned. As we added more compute and scaled up the cluster from basically 1,000 CPU all the way up to 50,000 CPU, we're running into now too many request exceptions in the container itself. We have some issues with job state. We have some issues with start time. We have issues with costs. So the first one is, I love this slide, because this is AWS 101. This is what they tell you to do if you're going to run an ECS container and you want to get a secret into that container. So if that ECS container needs to connect to a database, and you need to get a user ID and a password, and you store that into parameter store, and then you go get it. So when you're scaling up a couple hundred ECS containers, that's fine. When you start scaling up thousands, 3,000, 4,000, 5,000 containers, and you have this thundering herd problem, they're all starting at the same exact time, parameter store tends to fall over with too many request exceptions. And whether or not you want to do exponential backoffs or jitter or randomness to your retries, it doesn't matter. The gap between the number of requests that you're making and what parameter store can support is just too broad. So the solution here was to use S3. So in our case, we store our secrets on S3, which allows us to scale up to a level that we need to in order to support all of these containers starting at once. Then we also had issues with job state. So what is job state? Job state is that shared memory that's used across containers, and it's also handling job assignment. So think of this. You've submitted a job. It's spinning up 20,000 containers to analyze equities. The first container starts up and says, what am I supposed to do? The job state engine then responds and says, you're working on Microsoft, and here's the data that you need in order to work on Microsoft. Next container starts up, says the same thing to the job state engine. What am I supposed to work on? you're working on Apple, and here's the data that you need to work on Apple. And then it also deals with output and input. So when the job finishes, all of that information is stored in the job state engine so that it can be collected and returned to the caller. So we started this design using EFS as the job state storage. That quickly fell over. And it fell over because EFS was running into %IO limits, and we were basically pinning EFS, and the cluster was no longer responding. We switched to Redis, and then Redis fell over. Redis fell over because researchers started submitting data into the job state, and we ran out of space within Redis itself. And we've ended up finally settling on S3. This may look like, oh, we've moved from one service to another, and these services are not good for you. That's really not the case. Actually, the point of this slide is to show how easy it was to switch from one storage system to another with relative ease. So if I had to build this on premise and build out a scale-out file system and buy, let's say, Isilon and deploy that, and then find out, oh, that's not going to work, and now I need to switch to Redis, and oh, that's not going to work, and switch to another, it would have been months of delay. Whereas here, it was just a matter of days to switch from one to the other. Next thing that you want to monitor is job start times. So here is a histogram of job start times. You can see most of those jobs are starting within the first 2 minutes. I recommend that in order to reduce your job start times, you bake your AMIs with as much software as possible and leave as little into the runtime of the image start as you can. So we use Packer from HashiCorp in order to bake our AMIs. And we have a launch time from the initial EC2 launch to it now being able to access and run jobs of under 90 seconds. And then I also recommend that you give yourself an SLA for jobs. So our SLA is that a job will start within 10 minutes, 75% of the time, and 15 minutes, 90% of the time. And then as you notice there, we sort of have this long queue, that sort of long tail to the start times. I'm going to get into why that's happening in the next slide. So here we have the compute environment. You can see on the left-hand side, we have a number of vCPU that we're running. And then along the bottom there is a time scale. You definitely want to set limits on your cluster. So don't do unlimited compute. You want to set a limit for many different reasons. One, and probably the biggest one, is runaway costs. So if you allow your researchers to run basically at unlimited scale, you'll quickly run into a scenario of someone leaving a job running on a Friday evening, and then it runs all weekend long at 50 or 100,000 cores, and then on Monday morning you come in with that beautiful $1 million bill. That's always difficult to defend to the boss as to why you ran into that particular issue. The other thing that you may see if you start operating at scale is these little step functions going on here. So what's happening there is someone has submitted a job that needs 50,000 CPU, but Batch doesn't immediately scale you up to 50,000. Instead, it goes through steps. This has some good and bad. The good part of it is it reduces that thundering herd problem of everybody coming in at once. The downside of these step functions is it adds to that tail of start time. It leads to those longer starts of jobs. All right, takeaways. So follow Amazon best practices, use Spot, multi-AZ, log everything, monitor everything. So what you'll hear from any solution architect or anybody from professional services working with the Amazon team. Watch for scale issues. So eliminate API calls in your containers as much as you can. If you have to use an API call in a container, use only services that can scale. Things like DynamoDB, S3, services that you can turn a dial and make them go faster. Switch to event-based versus event and message-based versus polling-based for status. It's much easier to design and deal with events as they're flowing through a system than doing polls. And then choose your job state backend with care. I think when we developed this, we just sort of guesstimated that EFS would be the right solution, and I think we would have been better off if we had put more time into the upfront design. Write a lightweight wrapper around the AWS Batch API. You're dealing with a lot of non-technical people here. They're not developers, they're not engineers, and hence exposing the entire AWS SDK to them just doesn't make sense. They should have that trimmed down to just the APIs they need. And then buried in there, whether it's in Lambda functions or as part of that lightweight wrapper, put in your governator function, put in your guardrails in place to make sure that people do the right things. Reduce your start times. So use things like Packer, Netflix as a tool to do this as well, to pre-bake your AMIs. If you'd like, pre-warm your cluster during active times a day. It's another way to reduce the start times. So you can say, instead of being at 0 at 8 a.m., say, hey, let's start at 1,000 cores at 8 a.m., and then we'll scale up and down from there, and then at 6 p.m., scale it back down to 0. Give yourself and your end users an SLA for job start times. This is how they'll be judging you based on your performance, how quickly jobs get into the started state. And then last but not least, have controls for runaway costs. So alarm for long-running jobs. We mentioned previously that you can set a timeout on jobs. That's great. If you put that into your governator function to make sure that the timeout is always the hard timeout that's available in a batch, you can do it that way. You can also just monitor for it and alarm when there's a job that's been running for too long, or sort of outside of your window of expectation for a job to run. And then finally, set limits on your compute environment. Do not let it run in sort of an unlimited state. Make sure you set a cap as the number of CPU that you can actually execute. All right. That's it. Q&A. There's a microphone here if you'd like to walk up to that. For people that don't like to walk up to the microphone, I'm one of them. Ray and I will be here after the presentation outside if you'd like to talk to us one-on-one.
Thanks. The question is, with your child job within a job thing that you constructed, I'm assuming then that the parent job is waiting synchronously for the finishing of its child jobs?
That's correct.
Do you have a limit on how deep the child jobs can go?
No, we don't. They can go as deep as they'd like.
So a job could wait forever?
A job could wait forever, but eventually that governator function that's basically in place to make sure it doesn't wait forever would hop in and say, kill this job.
Thank you.
Hi, good presentation. Thank you.
Thank you.
Question about the data. So you deal with a lot of data, financial data, that goes into these containers that are split into many cores. Where do you store that data?
So the data is sort of all over the place at AQR. Some of it is back on premise. But for a latency perspective, we try to keep as much of the data in the cloud as possible. So our storage mechanisms are, today, they're EFS, and they're also S3.
I see. And the other thing about you talked about writing the lightweight wrapper, and I think that's what you called batch star.
Yes.
Is that something that you would ever consider open source?
We are considering open sourcing it. So just a fun fact here, if you're familiar with the Pandas library that was built and published by AQR, so we have a history of sort of open sourcing project. We also have a history in academia of publishing our results in papers. And now we're also getting into the sort of business of open sourcing more of our projects. This is one of the top projects that we're considering open sourcing.
Excellent, thank you.
Sure.
I was just wondering how you're handling client feedback if you have a client crash or anything that is a long-running job, how you're sending that information back to the client in those cases.
Sure. So there's a couple commands that are available to them. This command bstat, which is the equivalent of bstat, is available for them to check the status of jobs. There's also a command that we call blog, that you can then get your logs out of the job itself. And then last but not least, we also take all of the log output, goes into CloudWatch logs, and then we have a Kinesis connector to that that streams those logs down into our on-premise Splunk. So then researchers can go into Splunk and then parse and view the logs from there.
Thank you.
Sure.
Does AWS Batch have support for Windows at this point, or is there any plan?
Windows container, it's something that will be on our roadmap for 2019, yes.
Okay. And generally in high-performance computing, the concept is of a job and a task. Is there anything like a task with
So you can
batch?
think of AWS Batch job as the task. Are you using?
Is that the smallest unit of work?
Yes, that's the smallest unit. We also have a concept called array job, which if you submit an array job, you can have thousands, hundreds of thousands of child jobs. That's a single job unit. Array job is just a collection of jobs that you can submit all at once.
Thank you.
Thank you for sharing your experience. Question is more like like a compliance and like a security side. When you first had this idea to load your like research environment in the AWS, did you have to go through with the compliance?
Oh, of course.
Security.
Yes. Yeah.
Like, how was that experience? Can you share a little?
It was good. The security, the InfoSec team that we have is very understanding. It's not a team of just a flat out no, and then you have to sort of prove the yes that I've dealt with before with other InfoSec teams. They're very understanding of the business requirements. So here, AWS makes sort of perfect sense for these types of workloads. And then it was just a matter of working with InfoSec, the AWS team, and just convincing them that actually running in AWS is just as secure as running in on-premise. And then we have a bunch of controls that I didn't get into in this presentation. Things like you can't launch an internet gateway, you have to come on-premise to get access to the internet, you have to go through a proxy still that's on-premise, there's encryption at rest everywhere, there's all these long series of controls that are in addition to the controls that we had on-premise. So it's actually more controls in place in the cloud than we do in our on-premise data centers.
Thank you.
Sure.
Hi. Can you just mention a little bit more about the job state that you were storing in S3 and what workflow engine you were using or you wrote and how you dealt with that data?
Sure. So the workflow engine is written by me. It isn't very complex. So we basically serialize the job data and store it persistently on S3. And then each one of the jobs, when they start up, they understand how to deserialize that data and then determine where they are in the process of processing the job itself. So each one of the containers that executes gets an index ID, that's an environmental variable. So when he launches, when the container launches, he looks at his index, he looks at his container, the job state information, which is just basically a giant map, and matches his index to the hash in that map and says, oh, that's what I need to work on. That original sort of serialized object is created when the researcher actually submits the job. So when the researcher submits the job, that's when that job state is created and dumped onto S3.
Yeah, so that's like the graph, the DAG graph is in S3 then, right?
What's that?
The graph that is in S3, the compute graph?
The DAG graph is made by the code of the researcher himself. So he's the guy who's describing how that DAG should be created and the dependencies that should exist.
And then all your outputs are stored in EFS.
And all the, what's that?
The job outputs are in EFS so the researchers can go back and see it there.
That's correct.
Yeah, cool, thanks.
Sure.
So a question, today morning somebody announced, in the keynote they said there'll be Lustre, the Lustre file system for
Lustre
HPC.
Yeah.
You went through your traumas of going from EFS to Redis and so on. Lustre is something that we tend to use for HPC.
Yes.
Is there any plans for integrating batch processing with Lustre and potentially doing some forms of checkpointing which Lustre gives you so that if you reach a certain guardrail, you can then come back, stop the job, come back? any such features are going to be provided?
Yeah, those are two great questions. So the first one on EFS is, fun fact, right now the cluster is pinned at 100% utilization. EFS is hit its % IO limit. I happened to check before I got on stage and got the alert. So EFS is having a problem for us right now. Lustre may be the fix. Having experienced Lustre in the past, you have to load up your own clients. The implementation that Amazon seems to have, and this is all brand new. You're getting my opinion on the fly here. You have to copy the data from S3 and then do some funky commands to persist the data back into S3 with the Lustre connection. And I'm not sure how that's going to get exposed to a researcher. A researcher is just looking at a file system. He writes, he expects that file to exist when the Lustre file system is rebuilt again, and I'm not sure how we would end up doing that. So there are some issues there that need to be resolved. We are also exploring other file systems as well beyond just EFS and Lustre. I'm not going to name any names, but there are a lot of them available in the expo hall. And then on your checkpointing question, it's such a difficult computer science problem, right? Like to put those checkpoints in place and then to recover. It's not something that we have built as the cloud engineering team, but it's possible that the research engineering team, so we have researchers and then we have research engineers that help those researchers. It's possible that one of them is in the audience looking at me right now. It's possible that maybe one of those guys will build checkpointing as part of the job submission.
I just want to add one thing about Lustre, the FSX for Lustre. So it will work out of the box with Batch right now. If you use EC2 Launch Template, use the custom data, user data feature, you can mount the Lustre right now. But eventually we might implement something to make it easier for you to do it, right? Maybe a checkboxing. I want to create a file system when I launch a computing environment, something like that.
Specific set of drivers are needed for each of those.
Yeah, those drivers will be built into the AMIs, or you can install them on the run, the kernel drivers. Yeah.
Okay. So you mentioned when the researcher is doing the historical analysis for backtesting, so the data is stored in some on-premise and some on cloud and some on database and file systems. Did you had any issues with, when the researchers submit a job, they face access issues connecting with different resources, or it was all like
seamless? Yeah, so the number one thing is we basically said to researchers, look, if you're going to use this cluster in the cloud, that data eventually needs to move in the cloud. It's less an access issue. So to a certain extent, the data is sort of shared across the researchers. It's sort of how they do their business. But it needed to exist in the cloud. It needed to exist in scale. First, there's the latency from going from where we are in Connecticut down to North Virginia. Just to get the data would be an issue. But the other issue would just be at 50,000 cores or 50,000 vCPU, 25,000 cores, we'd most likely keel over anything that we had on premise.
Another question, maybe not related to this, like what is the database or structure that you use on cloud, which enables for the users to store the data there?
Oh, what do you mean?
So like on-premise, so you cannot connect due to the latency. So what is like, are they using some kind of Amazon Redshift, or like what are the different data structures that they use? Oh,
that's something that I can't share. But all I can say is that it's stored a combination of S3 and EFS in the cloud.
Okay. And another question, so when the user submitted a job, do you have any other tools that to monitor like visually, oh yeah, this is running, and are you just using the AWS batch, or is it only through the pipeline?
So there's the API that I showed to submit job, also has an API available to monitor jobs as well. And there's also that command that I showed quickly through one of the screenshots there, a command called bstat, where you can actually monitor the status of your running job. And then as well, there's logs that get outputted down to, can be picked up by one of the commands, but also can be picked up through Splunk.
Thank you.
Sure.
Hi there, thanks for the talk, it was great. I just wondered, do you treat your resources as a single cluster, or do you implement any kind of segregation between users, or and your limits?
Yeah,
as well?
that's a great question. So right now it's a single cluster. The goal was with the design that we could make the cluster big enough that no one would step on each other. What we're finding already is that people are stepping on each other. So in all likelihood, we'll start to divvy things up by department. Since we deliver everything as infrastructure as code, it's relatively easy for us to just stamp out another high-performance compute cluster and then send a set of users one way and another set of users a different way.
That sounds familiar. Okay. And just one other question. So I guess your actual framework for submitting jobs is quite opinionated in terms of what the researcher can run, right? So I guess they have to use that Python framework, and you can't run like arbitrary, other languages, arbitrary commands. Is that?
Yeah. So right now, most of them work in Python. The framework that you saw, the batch line, I did Python test my model. That just as easily could have been Java, run my jar file, or run this Go program. Like, it's ubiquitous from that perspective. The API itself, though, was written in Python. There isn't a plan yet to write it in any other programming language, but it's relatively easy to port to someplace else if we needed to.
Okay, thanks very much.
Sure.
Hey, oh no. Sorry, I completely.
It's all right. Any other questions? All right. Like I said, Ray and I will be around if anyone wants to come up and approach one-on-one. I'll be happy to answer anything you have.
Thank you, guys.
Thank you.